engines and universal rule. Every engine you've ever used, a car, a lawnmower, a jet, even the AC in your house, is fighting the same invisible rule of the universe. And no matter how advanced our technology gets, this rule always wins. Heat moves hot to cold. To understand it, start with something simple. Heat always moves from hot things to cold things. If you pour hot coffee into a cold sink, the heat spreads out. If you touch a warm laptop, the heat flows into your hand. Entropy, defined. This natural spreading out of energy is called entropy. It simply means that energy tends to spread out and become less concentrated, and that tendency is one of the most important ideas in all of physics. How engines use heat. Engines rely on this flow of heat. They take heat from something hot, use part of it to do work, and dump the rest into something colder. A car engine burns fuel, pushes pistons, and releases leftover heat into the air. A jet engine burns fuel, spins turbines, and blasts hot exhaust. Even your refrigerator works by moving heat from inside the fridge to the warmer room outside. Waste heat is unavoidable. But here's the catch. Because heat always spreads out, no engine can ever use all of the heat it receives. Some of it must always escape. This isn't bad engineering, and it's not a materials problem. It's a law of nature. Carnot limit introduced. There's a simple formula that sets the best efficiency any engine can ever reach. It looks like this. Eta equals 1 minus T sub C divided by T sub H. Eta means efficiency. T sub H is the hot temperature where fuel burns. T sub C is the cold temperature where waste heat goes. If T sub C gets colder, the fraction gets smaller and efficiency rises. If T sub H gets hotter, the fraction also shrinks and efficiency rises. No engine can beat this limit. It's built into the laws of physics. Hot versus cold days. You've actually felt this in real life. On a hot summer day, your car can feel sluggish because the warm air makes it harder for the engine to dump heat. On a cold winter morning, the engine runs more efficiently because the cold air helps pull heat away more easily. Power plants love cold. Power plants take advantage of the same effect. Cold air and cold river water help them get rid of waste heat so they can operate closer to their theoretical limit. That's why they often perform better in winter than in the middle of a heat wave. Absolute zero. Now imagine trying to make an engine perfect, 100% efficient. To do that, the cold side would have to be at absolute zero, the lowest temperature possible. But as things cool down, they slow and resist further cooling, and the universe never lets anything quite reach that final step. Perfect efficiency. Impossible. So perfect efficiency is impossible too. No matter what engine we design, there will always be some waste heat and some energy that slips away. Applies to fridges and AC. This limit doesn't just apply to engines. It applies to refrigerators, heat pumps, and air conditioners. Anything that moves heat around. It's why your fridge can't cool food instantly, and why your AC struggles and runs longer on very hot days. Why perpetual motion fails. It also explains why so-called perpetual motion machines, devices that run forever without losing energy, can't exist. They would need heat to flow backward, from cold to hot, without any effort. Entropy simply does not allow that to happen. Carnot. What's amazing is that this idea was discovered long before we understood atoms or molecules. In the 1820s, a French engineer named Carnot tried to design the perfect steam engine. He didn't have modern physics, computers, or even accurate thermometers. The efficiency wall. But he noticed something strange. No matter how he changed the design, every engine hit a wall it could never cross. That wall turned out to be the efficiency limit we still use today to judge how close real engines come to perfection. Real engines versus limit. Modern machines get closer to that limit but never reach it. A car engine might reach 30 to 40% efficiency. Jet turbines do better because they run hotter. and rocket engines run even hotter than jets. Yet all of them still fall short of the theoretical maximum. Universe takes its cut. The universe always takes its cut. No matter how clever the design, some energy is always lost as heat.